Hello and welcome to Dove Biology APES Lessons to Go. In this video we'll be exploring the mining of non-renewable mineral and fuel resources. As a result of consumption of goods and services, every American born will need about 3.7 million pounds of minerals, metals, and fuels within their lifetime. All of these items are things that we extract from our Earth's surface. The mineral resources are going to be concentrations of naturally occurring material in or on the Earth's crust that can actually be extracted and processed into useful materials at an affordable cost. In 2007, Virginia's non-fuel raw mineral production was actually valued at $1.15 billion, with crushed stone by value, Virginia's leading raw non-fuel mineral that's extracted. Ores are rocks that contain a large enough concentration of minerals, oftentimes metal, that can be used to make a profit. Most published estimates of the supply of a given mineral resource refer to its overall reserves. Now, a reserve can actually increase when we find new profitable deposits, or when there are new technologies developed that make it profitable to extract deposits that were previously too costly to extract. Now, minerals are going to be removed through a variety of methods that are going to vary widely in their costs, safety factors, and levels of environmental harm. We can generally classify these as either being surface mining techniques or subsurface mining techniques. One example of a surface mining would be open pit mining. Here, machines will dig holes and remove ores, sand, gravel, and stone. One of the drawbacks of open pit mining is you end up with basically a large pit, and toxic material can actually accumulate at the bottom. Another type of surface mining is a strip mine. Here, earth movers are going to strip away the surface earth, which is called overburden. And then these giant shovels can actually remove the mineral deposits. A major drawback of this, besides disturbing lots of land, is the overburden are oftentimes put into these big piles, which they call spoil banks. And these are highly erodible. And so any of the sediments that come off of these spoil banks can enter into waterways, reducing the potential for photosynthesis. And if there's any toxic material in those spoil banks, then that too can get into our groundwater and surface water supplies. Another type of strip mining is contour strip mining. This is used on hilly or mountainous terrain. Now, unless the land is restored, you actually end up having this huge, it's called a high wall, which is highly erodible. And so vegetation is going to have a hard time growing on this, and so we're going to lose a lot of sediment, which then can enter into our waterways, causing pollution. One of the most controversial forms of surface mining is mountaintop removal. Here, explosives and machinery will actually remove the tops of mountains to expose minerals like coal. The resulting waste rock and dirt are actually, coming off of this mining initiative and getting into the streams below and causing a lot of aquatic pollution. Now, in some cases, when you have a deposit that's really deep below the Earth's surface, we have to use a subsurface mining technique. Now, a benefit of this is that it disturbs much less, about 1/10 the land, and doesn't produce quite the amount of waste from surface mining techniques. Unfortunately, because you have to dig tunnels, you're actually going to get less of the overall resource. It's very expensive to do subsurface mining, and it's very dangerous to the miners that are going into the earth. Now, the mining processes and the use of mineral resources can cause a lot of environmental damage. Firstly, it uses an enormous amount of energy to extract the resource. It causes significant habitat destruction. Because we're disturbing, especially with surface mining techniques, a lot of soil, we can lead to significant erosion. And then the process can also cause significant air and water pollution. One source of water pollution from mining is acid mine drainage. As water moves through a mine, it could actually weather out iron sulfide and other sulfide compounds and produce sulfuric acid. Sulfuric acid then will leave the mine and enter into aquatic ecosystems. This reduction in pH can damage the aquatic system, as well as it can cause the leaching of toxic heavy metals that can further contaminate the aquatic life present in that system. There are some Roman mine sites in Great Britain that have continued to generate acid drainage 2,000 years past the time they were last occupied. Once our mineral-containing ore has been removed from the mine, removing the metal from that ore can cause additional impacts to the environment. Ore usually has the desired material and waste called gangue. Removing the metal from the gangue produces tailings, leftovers. Toxic metals from these tailings can actually blow away or leach into the ground and contaminate water sources. After separating the gangue from our desired material, the metal has to be removed from the ore. This can be done through heating, a process called smelting, or by using solvents to dissolve out the metals. Heating of our ore to be able to release the metal can produce air and water pollutants. The use of solvents like cyanide to extract gold can also produce pollutants and toxic wastes. The Surface Mining Control and Reclamation Act of 1977 is the primary federal law that regulates the environmental effects of coal mining in the United States. SMCRA created two programs, one for regulating active coal mines and a second for reclaiming abandoned mines. This is funded by a tax on mined coal. Now, half of the abandoned mine fees will fund reclamation programs. The other half are used by the Office of Surface Mining to respond to emergencies like landslides or land subsidence and fires, and to carry out high-priority cleanups. Now, the future supply of a resource depends on its abundance and how rapidly that supply is used. While we may never run out of any mineral, it may become what's called economically depleted, where it'll cost more to extract than it's worth. This occurs when we have removed 80% of that resource. Now, depletion time is affected by cost and efficient use of the resource. For example, if we just mine, use the material, and throw it away, and we don't find any new reserves of what we're trying to get out, we're going to deplete that resource very, very rapidly. If we recycle or increase our reserves, we're going to increase that depletion time. So the way that we can really make sure that a resource lasts a good long time is by recycling, reusing, reducing consumption, finding new reserves, and increasing our technology for extracting that desired resource. Scientists and engineers are developing new types of materials as substitutes for a lot of our metals, plastics, and composite materials. Recycling valuable and scarce metals will actually save money and has a lower environmental impact than mining and extracting them from their ores directly. Additionally, there's a new movement in industry. It's called the eco-industrial revolution, where industries can actually mimic nature by recycling and reusing a lot of their minerals and chemicals. Some industries can actually use a resource exchange where waste from one manufacturer becomes the raw materials for another, similar to like a food web in nature. Subaru, for example, has several zero waste facilities where materials from one process in manufacturing is then used in another place as a raw material, so they're sending nothing to the landfill. With your average American using 3.7 million pounds of minerals, metals, and fuels within their lifetime, it is imperative that we find ways to sustainably extract, utilize, and reuse these materials so that not only can we extend their life, so that these resources don't become economically depleted, but we also minimize our overall impact on the planet.